So in the previous lecture, we have seen how the ATM traffic can describe itself through the deterministic traffic descriptors, which is GCRA T tau, and today we will see how a network can have a simple admission control policy to determine whether these traffic sources with GCRA T tau parameters can be admitted or not. Okay. So essentially we would be asking this question that here is a stat mux, okay, as we are saying, here is a multiplexer which wants to give the quality of service guarantees, and we would be asking this question that how many GCRA T tau traffic, that let us say that this is like T1 tau 1 and GCRA T2 tau 2 so on till let us say GCRA Tn tau n. Okay, how many such sources can be admitted onto this output link, and let us assume that this output link has a capacity of C, and let us assume that this multiplexer has a buffer and it may have a scheduler which for the simplicity may be a FIFO scheduler. So the question that we are asking is how many GCRA T tau connections can go through these transmitters, can be admitted through this ATM multiplexers Now before we can answer this question, we of course need to know that what are the quality of service attributes, and so let us assume for the time being, to give you an example, that the quality of service attributes are the delay D. Okay. So in other words, we are asking the question that how many such GCRA T tau traffic can be admitted through a multiplexer, which is essentially a buffer with first in first out kind of a scheduling discipline. How many of such sources I can admit such that the packet delay is less than certain quantity, let us say capital D. Okay. Right now we are not assuming any other quality of service attributes like packet loss or so. Moreover, we are also assuming that these sources are homogeneous in nature. By homogeneous in nature, I mean that all these sources are described by the same GCRA T tau parameters, and at the same time all the sources have uniform quality of service requirements, that is the capital D. Okay. Now before we answer this question, we have to actually determine what is the fastest GCRA, what is the fastest sequence of cell that conforms to a certain GCRA T tau parameters. Now why fastest? Because if I transmit the fastest sequence of cells through a ATM multiplexer, which is basically a buffer with a transmitter which is transmitting at the rate of C cells per unit of time, then if I transmit the fastest sequence of cells, okay, I will have the maximum backlog. Okay, so I will have the maximum backlog, and whenever I have the maximum backlogs, I will suffer the maximum delay. So essentially I would try to find out what is the fastest sequence of cells, okay, that I can generate, which will conform to these GCRA T tau parameters. So all the results which I will be deriving will be for this fastest sequence of cells. Okay. So now what is the fastest sequence of cells? I say that a cell sequence of cell which is denoted by x1, x2 so on xk. So where x1, x2, xk, these denote the arrival times. Now we say that this is faster than another sequence y, which is having the arrival times as y1, y2 so on yk, if xk is less than or equal to yk for all k, then I say that this sequence is fastest. Now, how can you construct the fastest sequence which conforms to GCRA t tau parameters? Okay, so what do? We start at time 0 with our bucket full of t plus tau units of fluids. Okay, and then I generate a cell, so my capital T units will be decremented. Now, the fluid accumulates in my bucket at a unit rate. Now, as soon as capital T units of fluids gets accumulated, I generate another sequence and so on. So, if I keep doing this, then I will generate the fastest sequence of cell which will conform to the GCRA t tau parameters. Okay. Now, I am assuming that I have a fastest sequence of cells that conforms to GCRA t tau parameters. Okay. Now, this fastest sequence of cells, let us say if I transmit through a buffer, okay, which is equipped with a transmitter which can transmit with a capacity of C. So, we are saying C cells per unit of time it transmits. Okay. Now, obviously this fastest sequence of cell will generate the maximum backlogs. Now, we assume that if C is greater than 1 by T, okay, then the Q length or the buffer length will always be finite. Okay. That means the backlog will always be the finite. What I am trying to say is that the backlog will be finite because the transmitter is transmitting at a rate faster than the nominal rate of generation of the cells. Okay. Now, we assume to determine a simple admission control policy. Now, we assume that that there are n streams, n such GCRA t tau streams, and assume all these t tau streams are the fastest streams. Okay. So, they are being generated as per my explanation just I have given you, that the bucket is first filled at t plus tau units, then you generate a cell, you remove capital T units of fluids, and of course the fluid is continuously accumulating in the bucket at a unit rate. As soon as capital T units of fluids gets accumulated, you generate another cell and so on. So, this is the fastest sequence of cells. Now, assume there are n such streams which are generating such fastest sequence of cells, and now they are transmitting through this ATM multiplexer, which is basically a buffer equipped with a transmitter which is capable of transmitting at C cells per unit of time. Now, just now we saw that if we are transmitting a single stream, okay, then in order for the backlog to be finite, our requirement was that C, that is the capacity of the buffer or the transmitter, should be greater than 1 upon T. C should be greater than 1 upon T. Now, n streams are transmitting the same buffer. So, naturally, in order that the backlog is finite, our requirement should be C should be greater than n by T. Okay. So, now we would like to determine, okay, what is the an admission control policy. So, we are saying that n such GCRA t tau streams share a ATM multiplexer, or which is basically a buffer equipped with transmitter which transmits at C cells per unit of time. Remember, our unit of time here is the one cell transmission time. Okay, so that we have been always using it. So for backlog to be finite, we know that our requirement is that C should be greater than n by t. Okay, so now we would like to determine, okay, that how the network can admit such n GCRA t tau streams such that such that a certain delay guarantee is capital D can be given. So in other words, our objective is to determine what is the maximum value of n, okay, that is how many number of such connections can be admitted such that the delay is less than some quantity, let us say capital D. Okay, so now let us assume, to prove this or to determine this, and let us assume that tau is very greater than capital T. Then k plus 1 cells can be sent back to back by a single stream if in the period zero to k we have this quantity t plus tau minus kt plus k should be greater than or equal to t. Now why this? Remember, t plus tau, this was the amount of fluid which was there in the bucket at the beginning, right? So t plus tau was the now k amount of fluid entered into the bucket during the time 0 to k, right? Now since k cells have been transmitted, okay, kt amount of fluid would have been decremented, so that is why we have the minus. Now this is the amount of fluid which will be there in the bucket at the kth instant. Now this should be greater than or equal to t if you want to send k plus 1th cell. Okay, that means this should be greater than or equal to t if k plus 1th cell has to be sent, right? So this explains that k plus 1 cells can be sent back to back by single stream if during this period 0 to k if we satisfy this quantity. In other words, we can say that by rearranging this equation, we can say that maximum number of back to back cells which can be sent by a single stream m will be tau upon t minus 1 plus 1. Now this comes after rearranging the equation. Remember, after this single stream has sent these k plus 1 cells back to back, or in other words m cells back to back, after that the cells will come at a periodicity of capital T, because the fluid will get accumulated at a unit rate into the bucket. So the maximum number of back to back cells which can be sent by a single stream is this. Now let us say so this is by a single stream, and since that there are n streams are there, now each of these streams, okay, now maximum number of back to back cells is m, which I just shown that it is given by tau upon t minus 1 plus 1. Now there are n streams, remember. Now these n streams, each of them can send these back to back cells during the interval 0 to m minus 1, right? So these back to back cells are generated during the interval 0 to m minus 1. So what we are saying, that each of these streams, so these n streams, they generate these m back to back cells during this interval of 0 to m minus 1, and where m is of course given by tau upon t minus 1 plus 1. Now how much will be then backlog in the buffer? How much will be the backlog? Now the backlog will be how many packets have been generated, or how many cells have been generated, minus how many cells have been transmitted by the buffer. How many cells have been generated? Each of the streams has generated m cells. There are n streams, so how many cells have been generated? N into m. How many cells have been transmitted during the interval 0 to m minus 1 by the transmitter? The transmitter is transmitting C cells per unit of time. So therefore the transmitter has transmitted m minus 1 into C. Okay. So let us see how much is the backlog. Therefore the backlog is n cross m minus m minus 1 into C. Let us see an example where m could be, let us say, 4. So 0, 1, 2, 3. Okay. So the back to back cells have been generated are 0, 1, 2, 3, and they have been generated at that at this time during the interval of 0 to 3. But on the other hand, during the interval of 0 to 3, 1, 2, 3, that is m minus 1 into C cells have been transmitted. Okay. So where m is given by tau upon t minus 1 plus 1. Now suppose we want to say that we want to maintain a delay of capital D. Now a cell that will face a backlog of that faces a backlog of D cross C will experience a delay of D, right? Now suppose the backlog is D cross C, right? So a cell which sees that there is a backlog of D cross C, now the transmitter is transmitting at C cells per unit of time. So obviously that particular cell will have to wait for the time of capital D. Now if the maximum backlog is D cross C, then the cell will face a maximum delay of capital D, right? So now the maximum backlog, we have just determined that maximum backlog is n cross m minus C into m minus 1. Why that is the maximum backlog? The maximum backlog will be generated when these n streams are the fastest and they are also transmitting maximum number of back to back cells, right? So when the streams are the fastest and they are transmitting maximum number of back to back cells, then you will generate the maximum backlog, and if this maximum backlog is equal to D cross C, then a particular cell will experience a delay which will be a maximum delay of capital D. So let us now equate that. So what we are saying is that D cross C should be equal to n cross m minus m minus 1 cross C. Okay. So this is our governing equation, because remember that this is what is called as the maximum backlog. I can write this maximum backlog to be a function of t, tau, C and n. Okay. So this is the maximum backlog, and this maximum backlog is equal to this. So if I just substitute the value of m from this equations into this equations and rearrange these equations, then I will get this n is given by I get this equation that n is approximately equal to C into d t minus 1 plus tau upon t plus tau minus 1. So this is just by rearranging this equation. I am putting m, the value of m here, and then rearranging taking this C here and then rearranging, you will get these equations. Now remember, we had also said that these n streams, these n streams are conforming these n streams are transmitting to the buffer, and in order that this maximum backlog is finite, we also have the condition that C is greater than n by t. Okay, so now let's look at these conditions. What we are saying, n is given by this C into d. At the same time, we have that C is greater than n by t. Okay, so these are the two conditions. So in other words, we can write these two conditions as, in other words, we can say that we need to satisfy the condition. We can admit, n number of users for satisfying a delay of t, n into alpha of t, tau and d should be less than or equal to C, where alpha is equal to alpha t tau d is equal to maximum of d into t minus 1 plus, this should be maximum of t plus tau minus 1 upon d into t minus 1 plus tau into 1 by t. Okay. Now how does it come? See, remember this. So this is the quantity. This quantity is actually inverse of this. Okay. So if you see here, what we are saying that if you have to satisfy both these constraints, so in order to satisfy a delay, maximum delay of d, okay, with n streams sharing the GCRA t tau parameters, then the maximum number of n that can be there is this. At the same time, C has to be greater than n by t. In other words, n should be such that n multiplied by this quantity alpha, which should be less than or equal to C. Now what is the interpretation of this? The interpretation of this is, what we are trying to say is n multiplied by alpha should be less than or equal to C. Now let us say that these n streams were constant bitrate streams. Okay, they are all transmitting at the constant rate of R cells per unit of time. Alright, now they are transmitting at R cells per unit of time, and there are n such streams. So in order that the maximum backlog is finite, obviously we have to satisfy that n into R has to be less than or equal to C if they were the constant bitrate traffic. Okay. Now here on the other hand, what we are determining, we are saying that n into alpha should be less than or equal to C. So what is the significance of alpha? Significance of alpha is some kind of resources or the bandwidth, we can say, okay, some kind of an abstract bandwidth which needs to be reserved, okay, which needs to be reserved such that when these GCRA t tau n streams share this buffer, which is equipped with a transmitter transmitting at C cells per unit of time, the maximum backlog remains finite, and that maximum backlog is such that the maximum delay is bounded by capital D. Okay. So therefore alpha interprets the notion of some kind of bandwidth which needs to be reserved per traffic. Alpha is the kind of bandwidth which needs to be reserved per traffic flow, because there are n traffic flows. So alpha is the bandwidth which is to be reserved for each traffic flow. Alpha multiplied by n should be less than or equal to C, because C is the output link rate or the output capacity. So it means that alpha is some kind of a reserved bandwidth which is to be there for these variable bitrate bursty GCRA t tau traffic. So we say that alpha is nothing but an effective bandwidth. So we call alpha t tau d is some kind of an effective bandwidth of the source. Effective bandwidth of the traffic source which is having the parameters of GCRA t tau. Now this notion of effective bandwidth is very important in the communications networks. what we are saying that this effective bandwidth of course is a function of the traffic descriptor, which is GCRA T tau, but it is also a function of the quality of service attributes, which is delay, which is quite natural, because what essentially we are asking is that how much bandwidth we must allocate, okay, out of our C total bandwidth which is available, how much bandwidth we must allocate per traffic source which is having certain characteristics, in this case GCRA T tau characteristics, and at the same time it has certain quality of service requirements, which is, you know, capital D. So therefore, you know, it admits the notion of some kind of reservations per traffic source, and hence the name, which is called as the effective bandwidth. So what we are essentially trying to say that a network can have a very simple admission control policy if the network can estimate, or if the network can determine what is the effective bandwidth of the various traffic sources which are there. Okay. Now remember that this effective bandwidth is a function of the traffic characteristics and also is a function of the quality of service attributes that each flow desires to have. Now if given both these things, if the effective bandwidth of a traffic source can be determined, okay, and let us say the effective bandwidth of each source of ith source is represented by alpha I, then the network admits a very simple admission control policy, and that admission control policy is that sum of the effective bandwidths of all the sources must be less than or equal to the total bandwidth which is available with the system. So we have a very simple admission control policy, okay. So if we say that alpha I is the effective bandwidth of the traffic flow, effective bandwidth of flow I, okay, then we have a very simple admission control policy which says that sum of alpha I should be less than or equal to, you know, C, where alpha I, where the effective bandwidth alpha I is definitely a function of traffic characteristics and as well as the quality of service attribute. Now remember that this is very similar, this admission control policy is very similar to the admission control policy which we follow in a circuit switch networks. If these traffic sources were to share a circuit switch networks, then obviously we need to guarantee that sum of their peak rates is less than or equal to C, okay. So which is Pi is actually the peak rate. So in circuit switch networks the policy will look something like this. Now obviously you can see that the number of traffic flows which can be admitted in a statistical multiplexer will be much more than in the circuit switch networks, because we are admitting the sources based on their peak rates, okay. So naturally, because the effective bandwidth is little less than the peak rates and slightly more than the average rate, you know, typically the effective bandwidth will lie between the peak rates and the average rate. And the challenge really in the network's admission control policy is to determine the effective bandwidth of each traffic sources, okay. So now let us come back again to the effective bandwidth of GCRA T tau parameters that we had just determined, which is given by T plus tau minus 1 D into T minus 1 plus tau, okay, and 1 by T. Max of this we need to take, and this is the effective bandwidth of the GCRA T tau parameter. In terms of M, we can rewrite this equation as in terms of M, I can rewrite this as alpha T tau D is given by max of M upon D plus M minus 1 and 1 by t. So if we say that if d is very less than m, that means our delay requirements is relaxed, okay, then if the delay requirements is stringent because d is much less, then alpha t tau d is close to 1, okay. So you can see actually that the effective bandwidth of a traffic source, increases if the delay requirement decreases, okay. So as the delay requirement goes down, the effective bandwidth increases. On the other hand, if the delay requirement increases, then the effective bandwidth decreases, okay. Now in terms of ATM forum recommendations, just to say that in terms of ATM forum recommendations, remember that in an ATM forum a VBR source is represented by, so T has an interpretation of the R by, this is line rate divided by the sustained cell rate, tau has an interpretation of burst tolerance plus cell delay variation tolerance, and of course we have the D. So so we can write this the effective bandwidth in terms of these parameters R by SCR, burst tolerance plus cell delay variation tolerance into D is given by max of beta plus 1 upon beta plus D is lambda, where lambda is really nothing but SCR by R, and the beta is nothing but burst tolerance plus cell delay variation tolerance divided by R upon SCR minus 1. Okay, so here you can see that as the delay is very small, if the delay is very small, then we have the requirement which will be close to lambda, that is the SCR by R. Now we have seen essentially that how we have determined the effective bandwidth of a GCRA T tau traffic source. Now the problem, however, is that that most of these traffic sources are statistical in nature. Now what we are saying basically is that a source first determines what are the parameters of T and tau which suits him, okay. So that this is the responsibility of the traffic source characterizations. Once he determines that, then he asks, he supplies these traffic descriptors to the network's admission controller, and also the quality of service attributes. Okay. Now from these, the network determines whether the call can be accepted or not by determining the effective bandwidths. Okay. Now the source, the traffic source, actually puts this GCRA T tau traffic shaper or so in front of its traffic source at the source, and at the same time it will put it at the network to monitor the traffic, whether the source is conforming to these advertised traffic descriptors or not. But the problem really is that how does a source choose these T tau parameters, because that's clearly and unanswered questions by now. We have not yet answered how does a source will choose these parameters T and tau such that it accurately represents its traffic characteristics. The difficulty is that you can always choose the parameters of T and tau such that the network will be over provisioned because of that, because you can always choose those values closer to the peak rate representation of the traffic source, but we don't want to really do that. But on the other hand, we can if you choose such values of t and tau, that the traffic characteristics itself gets distorted substantially, because the traffic has to pass through these GCRA t tau traffic shapers, then obviously there will be a distortion that will get introduced to the traffic source itself. We will answer these questions later, okay, in the context of when we discuss the issue of quality of service guarantees in the internet. I will take up these problems later, but for the time being, let us ask this question, that if the source is statistical in nature itself, then how do we determine the effective bandwidth of such a source? Because we have just now seen that the network will admit a very simple admission control policy if we can determine the effective bandwidth of the traffic source. Because if we determine the effective bandwidth of the traffic source, then in order to determine how many number of users can be admitted, the policy is very simple. You just determine that the sum of the effective bandwidth of the traffic sources is less than the channel capacity, right? So now assume that the source is actually now statistical or bursty in nature. So we will see that how do we handle now the bursty random sources. Now our bursty random source is a source which is represented by AT, where AT denotes the number of bits or the number of cells, number of bits generated during 0 to t interval. This could be, number of cells also, if we discuss this in the context of the ATM. So what will be the average rate of a source? The average rate of a source will be approximately equal to AT plus t minus AT upon t for very large t. So if t is very large, then the average rate will be closer to AT plus t minus AT upon t, and let us say that lambda is this average rate. Okay, so now what we are saying is that here is this fluctuating traffic source which is coming, essentially AT, whose average rate is lambda, and it is sending traffic here, and we have C bits per unit of time, or C cells per unit of time, whatever it may be, and let us say that C, the transmission rate is greater than and lambda. Okay, so if the transmission rate is greater than lambda, then the probability that A t plus tau minus AT is less than or equal to CT for some large values of t, okay, where t is very large, will be very high, right? That is, the number of bits that have been generated during this interval t is less than or equal to CT, will be extremely large. Okay, now assume in our case, assume that CT for all t greater than 0, then we would try to prove that buffer, which is this buffer cannot remain non-empty, okay, cannot remain non-empty for buffer. We would try to prove this proposition, that buffer cannot remain non-empty for t consecutive time units. Okay, now how do we prove this? That at time t, let us say, buffer is empty. Let us say that at time t, this buffer, this buffer is empty. Then we would like to prove that it cannot be non-empty at t plus t, where t is such that a t plus t minus a t is less than c t for all t. Okay, so we are already admitting a substantially large value of t. Okay, now during this interval, how many number of bits that have been transmitted? Number of bits which have been outputted is c into t. Okay. Now since the buffer is non-empty at t plus tau, now assume that the buffer is non-empty at c plus tau, then the number of input bits which is equal to a t plus t minus a t. Now if the buffer is non-empty at t plus tau, then obviously if buffer has to be non-empty, then a t plus tau, a t plus capital T minus a t has to be less than or equal to c t. But this is a contradiction, because we have assumed a t plus t minus a t is less than c. So obviously the buffer cannot remain non-empty for capital T consecutive time units. Okay, that means what is the implication of this? That this scheduler would delay. So what we are trying to say is that at time t the buffer is empty, so it cannot be non-empty at time t plus capital T. Now the number of bits which have been outputted during this interval is c into t, and the number of bits which have been inputted are a t plus capital T minus a t. Now if buffer has to remain non-empty during this interval, if buffer has to be non-empty at capital T plus t, then obviously the total number of input bits, which is a t plus capital T minus a t, has to be greater than or equal to c t. Okay, but this is less than, but given is a t plus capital T minus a t is less than c t. Now this is therefore a contradiction, and hence we can say that buffer cannot remain non-empty for capital T consecutive time units. So what is the implication of this? What we are trying to say is that our bursty random source, which was transmitting, which was getting transmitted through a buffer which is equipped with a transmitter which is transmitting at the rate of c. Okay, then the scheduler or this transmitter would delay the packets by at most capital T. It will delay the packet by at most capital T, where we have carefully chosen the transmitter rate c in such a manner that it is greater than the average rate. Okay, and what is the definition of the average rate? Definition of the average rate is that average rate is approximately equal to a t plus capital T minus a t upon capital T. So for a very large value of capital T. Now what we are trying to say therefore is that it may be possible to reserve a certain portion of the bandwidth a little larger than the average rate, such that we can guarantee certain delay bounds on the traffic which is coming into this buffer, which is transmitting at a rate slightly larger than the average rate. Okay, now slightly larger than the average, how much is that average rate is actually as I already told you, that we need to determine basically the effective bandwidth of the traffic source. Now the effective bandwidth of the traffic source definitely depends upon the traffic characteristics and so on. So now I can just give you some example of to understand actually how these effective bandwidths are derived. I can just give you one small example and try to explain how we can determine, although we will not go into the detailed proofs of the derivations of these effective bandwidths, and then we will come back again to the discussion on how to select an appropriate parameters of the GCRA T tau. So let us consider a model which is where we are considering the traffic source to be a fluid traffic source. Traffic source is a fluid traffic source. Now this is clearly an approximation for the packetized traffic source, and this is, so this fluid is actually transmitting into this buffer, which is equipped again with a transmitter which is transmitting at maybe at C cells per unit of time, and so on. Okay. Now we assume this fluid to be a Markov modulated fluid. Okay. So this is fluid is Markov modulated fluid, which is called as MMF. So a Markov modulated fluid is actually where the rate is actually a function of a continuous time Markov chain. It is a function of continuous time, continuous time Markov chain. So we have this rate R, which is a function of Zt, and this Zt is a continuous time Markov chain on finite state space Z with certain rate matrix Qij, where Ij belong to this Z. Okay. So what we are saying is that this Zt is actually a continuous time Markov chain. It may go transition from state I to state j with rate matrix which is given by Qij. Okay. And when it is in the state I, the fluid may be transmitting at a rate which is a function of that state I. Okay. So that's, with this we are saying that the fluid or the rate which is transmitting at the state is actually as a function of that state, and the state itself is evolving as a continuous time Markov chain, and that is why we call it to be a Markov modulated fluid. Now this Markov modulated fluid is transmitting through this buffer. So naturally our question really is that if this buffer occupancy is denoted by xt, okay, so our problem really is we would like to determine that what is the buffer occupancy, and let us say that this buffer occupancy is denoted by xt, and the question that we are asking is that what is the probability that xt, this buffer occupancy is greater than x. Okay. So so this distribution we would like to know. Now again I would like to show you this is the Markov modulated fluid. Now this fluid is, it's like this, that the state changes from I to j. Okay, this is the state I, this is the state j. When in the state I, the source may be generating the fluid at a rate of Ri. When in the state j, the source may be generating fluids at a rate of Rj. This is a transmitter which is transmitting at the rate of C. Okay, and the question that we are asking is that what is how the buffer occupancy evolves. Okay. Now I am not going to give you the proof of this, but it can be shown that this distribution, the occupancy distribution of the buffer length Q length, is given by summation of Z, okay, Az into e raised to power minus beta z into x, where Az are of course the coefficients which are functions of the state z, and beta z happens to be the eigenvalues of this matrix A, and this matrix A happens to be having the components as Aij for I and j belonging to this state space Z, and Aij itself is given by Qij, where Qij is the transition rate Rj minus C. Okay. So now this gives the complete distributions of the buffer occupancy. Now obviously this is a little complicated expressions, so we can look for certain approximations. So we say that okay, let us approximate this buffer occupancy distribution by, we say that probability that xt is greater than x, that is approximated by k into e raised to power minus beta x, where beta is the smallest of the eigenvalues of this, and k is the corresponding coefficients. Okay, so what is beta? Beta here, so we are saying in the approximations, probability that xt is greater than x is given by k into, so this is approximated by k into e raised to power minus beta x, where beta is the smallest of the smallest eigenvalue, of this matrix A, and k is the corresponding coefficient. Now how to determine k? The k itself, you know, will depend upon all the eigenvalues of the A. So k itself, you know, the coefficient k itself depends on all eigenvalues and eigenvectors. So to determine k itself, we will require all the eigenvalues on eigenvectors of A. Of this matrix A, right? Now just take an example, just take a small example to give you a specific idea. Now let us say that this R zt, you know, which is the sum of the rates of n independent and identically distributed sources, n IID sources, independent and identically distributed. Each source is an on-off Markov fluid. Okay, so each of these sources are independent. Okay, by independent I mean each of these sources are independent. There is no dependency between them, and each of these sources are identically distributed, which is an on-off Markov source. Okay, so we say that Q01, so they have two states, 0 and 1. The transition rate from 0 to 1 is given by lambda, and the transition rates from 1 to 0 is given by mu. Okay, so now our Qij matrix, you know, that we had considered, our Qij matrix is given by this Q01. So Q01 is lambda and Q10 is mu. So here Z was considered to be the finite state space. The Z was considered to be finite state space. Here it has only two states, 1 and 0. Now it can be shown that, and I am not again going into the detailed derivation of these sources, it can be shown that for this when we want to multiplex the n independent and identically distributed sources, which is again, as I said, on-off Markov fluids, where the transition rate from 0 to 1 is given by lambda and the transition rate from 1 to 0 is given by mu, we can determine the value of k and beta explicitly, and the value of k and betas are given by this 1 plus lambda minus n lambda upon c upon 1 minus c by n, and the value of k is given by this. Now remember that to compute the value of k, we require all the eigenvalues of the matrix A that we had just seen. But if we compute the value of k and beta, then we know that what is the probability distribution of the buffer occupancy. Now note that the probability distribution of the buffer occupancy, this probability that the queue length is greater than x will decrease exponentially as x increases. So if we can fix the value of x, if we know that what is the maximum buffer length that we want, then from that we can determine the value of beta, and if we know the value of beta that we should keep, then from that we can determine that what is the value of C that we should have. In other words, we can actually determine what is the effective bandwidth of a Markov modulated fluid source which in this particular example we have said on-off sources. So what we are trying to say is that there is a Markov modulated fluid MMF source which is transmitting its fluid into a buffer which is equipped with a transmitter, and the transmitter is transmitting at the rate of C. Then we would like to know that what should be the value of C, and what is C? C is actually the transmitter rate that we should keep, such that the buffer occupancy remains less than or less than or equal to a certain quantity, or the probability that a buffer occupancy increases above a certain limit is extremely small, it is within the tolerable limits, and that way we can determine the effective bandwidth. But we are just seeing, to determine this we were relying upon the traffic characteristics of the source. We knew that a source is an on-off Markov source, which is mostly an approximate description of the VBR traffic. Particularly the video sources have been modeled using on-off sources. We will go into the discussion of what are the traffic modeling for various sources later, but I thought I would just give you an example of how we can determine the effective bandwidth of a statistical source. We had seen how we can determine the effective bandwidth of a deterministic GCRA T tau source very clearly, okay, and we can also see how we can determine the effective bandwidth of a statistical source.